So folks, Prith has an accomplished background, and I'm just going to share a lot of that with you. So he was the CTO of Ansys, which is now a company that, as of last week, merged with Synopsys. And he's responsible for driving the long-term technology strategy there. Prior to that, he was the CTO of Schneider Electric, CTO of ABB, managing director at Accenture, director of HP Labs, spent 20 years in academia as professor, chairman, and dean at UIUC and Northwestern. He founded 2 EDA companies, AccelChip and Banerjee. He served on the board of directors of Cray, Cubic, and Turntide, fellow of the AAS, ACM, and IEEE. He's received a BTech in electronics engineering from the Indian Institute of Technology, Kharagpur, and an MS and PhD in electrical engineering from UIUC. In addition to this, I wanted to share a little bit about AccelChip, actually. So Prith, as I was reading your book, so Prith has an amazing book called The Innovation Factory. I highly recommend you to get it. And I think if you read the book, you'll see that the JuliaHub journey has been exactly how Prith outlines companies can be built about academia, government funding, venture capital, and customers. But interestingly, in your first company, AccelChip, Prith, you built the Match compiler, which was MATLAB for FPGAs, and we see I at least see a lot of parallels with what Alan and I did back with our work, focusing MATLAB on parallel computing, and out of all of that work came out Julia. So we actually share a little bit of the path that has brought us together here. So without further ado, please clap for Prith.
Thank you very much, Viral, for welcoming me here. I'm absolutely excited to speak here today. And the topic is on digital twins, which is a very, very interesting, exciting topic, very interesting from an academic perspective, interesting from a business perspective. And originally, when I signed up, I was going to give a talk as CTO at Ansys, but now 3 days ago, I joined the executive leadership team of Synopsys. And so I'm going to speak, so I had to change the format of my slides to Synopsys last night. So the agenda is I'm going to first talk about the Synopsys Ansys introduction, because it's a really interesting thing that is going on in the industry, and I want you to know why these 2 large companies got together, right? And then dive into the technical topic of digital twins, how it is relevant to various industries like automotive, aerospace, energy, and so on. And then go into the core technology, right? So there's 2 broad approaches, data-driven approaches and physics-driven approaches, and sort of the hybrid approach which we do. And then I'm going to talk about some of the key innovations that are going on in this general area of digital. And then I will end my talk about the future of digital engineering, which is, I hope I can get to these things, because I'm painting a picture of what's out there, right? And again, I'm honored to have people like Alan and Bob in the audience, because this is the picture that I'm painting on behalf of the Ansys, Synopsys, Dassault, Siemens. We are all actually going in that direction. So I want you all to see where the world is headed. And I will tell you upfront, JuliaHub is going to be a very, very important part of that journey. So that's basically the thing, that the future is digital twins, digital engineering, and what this community is building, JuliaHub, is going to be a most important part of that journey. So with that, let me begin with what just happened last week. So 18 months ago, year and a half ago, Synopsys, which is the leading electronic design automation company in the world with about $6 billion in revenue, decided to acquire Ansys, the leading simulation company with about $3 billion. The question is why? In the world of electronic design automation, right, when you're designing electronic chip, like the NVIDIA's Blackwell GPU chip with 300 billion transistors, that requires electronic design automation. I mean, when I was a professor at the University of Illinois in 1985, I used to teach students how to do custom IC design, where on an IC you have masks. You have a red rectangle, which is polysilicon, and when you draw a red rectangle polysilicon over a green rectangle, which is diffusion, it forms a transistor. Those are the two mask layers that if you do it. Now, with that technology, you could design maybe 100,000 rectangles, so 10,000 transistors. So early part of VLSI design was computer-aided design. You had to design the transistors, the layouts, and the chip. Then the world of automation came in, where you essentially took standard cell designs like an 2-input NOR gate, 4-input NAND gate, and you entered your design not in drawing rectangles, but you enter it at the gate level. And then you use a automation tool like a placement tool, a routing tool to connect it up, and that's how you generate the rectangles. Then the technology went to RTL synthesis using technology like design compiler, and you say, okay, now enter it at RTL, VHDL, Verilog, languages like Julia, right? And push of a button gets the netlist of gates, push of a button gets the rectangles. And then there was high-level synthesis, which is what I did when I was at Excel chip, right? Taking high-level languages like C or Fortran or MATLAB and generate the RTL, VHDL, generate the get this and so on. So this is the world that Synopsys has been leading, right? All these semiconductor companies, the chips, when you design them from Intel, from AMD, from NVIDIA, from Broadcom, Qualcomm, so the top 200 companies that are designing chips, they use Synopsys or Cadence. Those are the two big companies that do it. So that's the world of electronic design automation. In the world of systems, when you are, I'm sure you came driving a car or flying an airplane or powered by the energy of a wind farm or a solar cell, or you are using some kind of a pacemaker, I hope not, but if you, so in all the industries like automotive, aerospace, energy, industrials, high-tech, and healthcare, that world uses, you need to design and you need to simulate. Ansys is the leading simulation company. And so the combination is, it turns out that on a Boeing airplane, right, that is, now it is no longer only the airfoil and whatever, right? There's a lot of software that is driving the airplane stuff, right? On a Tesla car, there's 100 million lines of code on a Tesla car, right? So it's a hardware-software combination ecosystem. So the world is moving towards hardware-software systems design, right? And while Synopsys was focused on only the design of a chip, Ansys was working on the system, bringing it together. We are now going to help customers build silicon to systems. So that is literally why Synopsys paid a lot of money, $35 billion, to acquire Ansys last Thursday. So because of it, now essentially you have the number one EDA company, which is Synopsys. Number two is Cadence. Number three is Siemens EDA, formerly Mentor. Combined with silicon IP, when you design a Blackwell chip, right, you don't design all 300 billion transistors from scratch. You say, hey, I need a HBM design. I need a PCI Express. I need an Ethernet controller. Bob, all the technology that you built, right? These are predefined IPs. I need a GPU core. I need a CPU core. I need an ARM. All of those things you put together, right? So Synopsys is actually the number two silicon IP provider. Number one is ARM. Number two is Synopsys. And number three is Cadence. So, and when you're designing these chips, you need to have the electronic design automation, and you also need the IP. Now you combine it with systems. This is a very, very interesting combination, and it's today a $9 billion revenue company. We had our executive leadership meeting yesterday, and we are literally going to change the world to do silicon to systems. This is our vision. So in that vision, we will see that JuliaHub will play a big role, and hopefully I'll get to that point. So now the technical part of the talk. So this is about digital twins. What is a digital twin? You have a physical asset like an airplane, right? This is the thing that is there, right? Or the engine on an airplane, or the car, or the engine in the car. Whatever is the physical asset, that's a physical asset. And then you have a digital model of that thing, right, in the digital world. And so sometimes people say, oh, a digital twin is just a simulation model. No. It is a simulation model, but that model is connected to the physical asset through, I put some sensors on that asset, right? And I collect data through an IoT platform, et cetera. And there's two-way information flow that happens. So you say, here is an aircraft engine. It is getting overheated. Oh my God, it's getting overheated. What if I could cool it down? I put cold water here. I do oil there. So I do all these what-if scenarios. So I do those what-if scenarios on the digital world. I say, oh, I should put a mixture of oil and vinegar or what, some random thing, right? And based on it, you make the decision, you do it, and you do it in the other part, right? That's what a digital twin is good for. And those of you who I know have watched the movie Apollo 13, that disastrous thing that happened, right? When people were stuck up there, right? NASA created a digital twin model of those things and said, oh shoot, how do I going to bring those people back? I put oil, vinegar, this, that, etc. Did all those things on the digital model. If I did this, we'll bring the astronauts back. So the concept of digital twin actually came out of NASA, right? So this that is the origin, but this is kind of what digital twins are. So digital twins allow you to track the past, deeper insights on the present, and predict the future. If we can say, this airplane is going to crash if you don't do certain stuff. This thing is, so if you could predict that with high accuracy, you can literally solve the world. So it turns out that digital twins, even though it started with NASA's stuff, right, is now used in aerospace, that aircraft engine, like GE's basically they do predictive analytics of that airplane engine, right? These are normal things, you all own cars, right? You are supposed to do tire rotation every 5,000 miles or kilometers, right? Why do you do that? Because statistically speaking, if you drive your car normally, right, you're doing this, that wear and tear of the tire will be such that if you don't screw it, change it, you will have a tire burst, right? You have to do an oil change every 5,000 miles. Statistically speaking, if you don't do it, it'll mess up. But practically speaking, if you look at Prith, I drive like a madman, right? My tire, if I don't rotate it every 4,000 miles, if I don't change my oil every 2,000 miles, my car is going to explode. This digital twin on Prith's car will monitor the oil pressure, my tire things, etc., and say, hey, it's time for an oil change, time for whatever. And if I can do this accurately, instead of that $400 million airplane crashing, I will prevent that crash. So that is why having accuracy of prediction of a digital twin in aerospace, automotive, manufacturing, buildings, oil and gas is so important. Now, digital twins has been used in different phases, right? So in the product design phase, in the manufacturing phase, in operations phase. Let me give you an example. GE engines, aircraft engines. You all fly planes, Boeing planes, etc. You have those little engines there, right? The blades going around and so on. So when GE engineers design that engine, right? There are 52 blades on the engine. They have to have exactly that curve. So it's a perfect, ideal CAD model of that blade. Now you try to manufacture the blade using injection molding or whatever, that blade, which is such a beautiful picture with a circle and a spheres and so on, when you manufacture it, it's a slightly different blade, right? So now you have a digital twin in the design, ideal world. Now you manufactured it, it has all the imperfections. So every engine of GE in the actual manufactured world is slightly different, right? So literally, if you could track every one of the engines, and that's what they'll really do, with some sensors, here is how I designed it, here's how I manufactured it, I can track how that engine will work. And now this plane is an Air India plane flying from Mumbai to Ahmedabad to whatever, and it's all the suits and whatever, flying into China, doing this. So that same aircraft engine on United Airlines, only flying between San Francisco, New York, clean places versus sort of Mumbai and Beijing, right? That airplane engine is quite different after 20 years, and then a bird strikes that engine, right? So now that engine is slightly different. So in the operations phase, even though you started with a perfect ideal world of a CAD model, in the operational world, it got all messed up, right? Because there's a little bend there. So I need to predict through the digital twin, the model of that aircraft engine in the design phase, in the manufacturing phase, and so on. And you can do it beautifully through the world of simulation, powered by JuliaHub, which is where I'm getting to. So now there is sort of two broad approaches to digital twins. One is you say, okay, here is an engine, right? And that I will put some sensors on the engine. I'll just measure the pressure, temperature, whatever, etc., on that engine, on this blade. If I could put sensors on everything, right? And collect a lot of data. And so if you collect a lot of data, it's just that time series data, pressure, temperature, etc., and you build a model. All the AI stuff that you see today, right, is basically doing that. Data-driven modeling, that approach is totally general. It doesn't care about the physics. You do structural physics, you do electromagnetic physics, you do fluids physics. Everything can be captured by data. The trouble is, so it is very general. The trouble is it requires incredible amount of data to train that model, right? Like million times of data. If you capture it, then you will predict exactly how that aircraft engine will work. The other trouble is it will only train it based on what it has seen. So if it has seen his aircraft going from San Francisco, New York, going from this to this, etc., it will never be trained to go into the streets of Mumbai with all the suit and so on, or whatever in Beijing, right? Because it has not seen that data. If it has not seen a bird strike, it will never be able to model the bird strike. But the bottom part is if you do simulation-based modeling with Ansys mechanical, here is this model of an airplane wing. Here is a bird that struck it, right? With LS Dyna, I can model exactly how much it will bend and whether that blade got cracked or not. It's physics-based simulation. So that is, I mean, it's like the ultimate thing, right? Because physics doesn't lie, right? The world around us is governed by the laws of physics. If I say this plane is going to fly, it will fly. If Fluent says this thing is going to fly, if it's going to stall, it will stall. I mean, I kid you not, because it is so accurate, because the world is following second-order partial differential equations, Navier-Stokes equations, or Euler equations, or Maxwell's equations. That's what we do in the physics space. The trouble is, that takes a long time. You try to model a bird strike, right? This thing, bird is striking this thing, it's like 10,000 hours, right? Or should I need the result every second? I cannot. So then what you need is you take that simulation model, you have to build what is called reduced order models. Don't do the simulation at the level of the 1,000 million finite element method, but you reduce those orders from 10,000 million to 1,000 so that you can run it really fast. So there are these two broad approaches, and where we have landed is you need to do hybrid. Take the best of both worlds. Do data analytics to do the sort of easy cases, and then correct it through simulation, right? So the intuitive explanation is the following. Suppose you had a bridge, right? And there's a 6-inch crack on the bridge. Statistically speaking, of all the bridges in the world over the last 30 years, right? When you had a 6-inch crack in the bridge, within 18 months, that bridge collapsed. Statistically speaking. That's what our insurance companies, State Farm says, hey, based on all the people who are driving cars, right? If you are male, you have this risk. If you are female, you have this risk. If you are a male who is crazy like Prith, you have this risk. So they are putting it in a bucket of a risk, right? That's statistics. So that bridge with that 6-inch crack would, statistically speaking, will crack after 18 months. Now, if you could put a sensor on that crack and you monitor the crack, and now use Ansys simulation to do crack propagation. If I have a 6-inch crack on his bridge and I have 1,000 cars going on the bridge with all the stress strain that is going on, I will predict that crack will be 18 inches in 6 months. Pure simulation. Now I actually monitor what happened to the crack in 6 months. If the crack is 24 inches, I say, oh shoot, I have under-simulated, so I need to push it, right? Push that simulation. Or if the crack was only 12 inches, I need to under-simulate. So with simulation, I predict that, and then with the actual measurement, I bring it down. That is intuitively what is going on with hybrid. There is a lot of math with the famous professors here will know, but I'm just giving you the intuitive explanation of why hybrid digital twins work. So we have sort of put together at Ansys, now Synopsys, this overall view of digital twin. So you have to start with the assets. The assets are the wind turbine engine, the car, the aircraft engine. You name the asset, and you put some IoT sensors on the asset. You collect a lot of data. You put it on the cloud, on AWS or Microsoft, whatever, right? Then you do data level analytics, which is what, as I said, most people, when they start doing digital twins, that's what. When I was CTO at ABB, CTO at Schneider, this is what I did to those companies, right? They have a lot of assets, robots, switches, transformers, and so on. I just created this ability platform or EcoStruxure platform, build the digital twins. So ABB could say, this robot is about to fail, and let me send a repair person to fix it, and if there's an accuracy. Then I came to Ansys and say, hey, let's do simulation-based or hybrid, and we'll do the accuracy. So what good is this digital twin? What it is it allows you to create virtual sensors. So if you could put a sensor on every part of the blade on a G's engine, right? There's 52 blades, and on that blade, you got to put it here, here, here. You could analyze the heck out of that engine. What is going to happen? The trouble is, if you put all those sensors, that engine will not work as an engine, right? Because you're doing an invasive change in that thing, right? Or you have a large oil well, right? It's 5,000 kilometers of oil wells and so on, right? And you're putting a sensor at every meter, every inch, every whatever, right? You could do all kinds of predictions. Unfortunately, that is not real. So in the world, what you can do is you can do virtual sensors, meaning just imagine a pipe. The pipe has oil coming in from this side, and the pressure, temperature, velocity of that thing is here. Now, if I had a sensor after 1 meter, it would measure this, because through fluid simulation, I can predict, because, hey, this is a pipe, this is a fluid flow, etc., with all this turbulence and so on. It has this pressure, temperature here. If I had a sensor, this is what it would measure. But I cannot have a sensor, so I'm creating a virtual sensor. At the first meter, second meter, third meter, fourth meter, fifth meter, at the 100th meter, I actually put a sensor to say, hey, did I do it right or did I screw up? No, you screwed up, Prith. You need to correct it. So that's how you do virtual sensors. So to measure missing data, to perform what-ifs, right? So here is this Apollo 13 sort of up there, screwed up, right? And how am I going to bring it down, right? I have to do, if I did this, oil and vinegar plus this, then this is going to work. So all those what-if scenarios you do in the digital twin, digital world, and then based on that, I make a decision, apply it. Do very accurate predictions. Hey, this bridge is going to crash. Today is Wednesday, July, whatever, 23rd. It will crash on July 28th. If you could predict that so well, my God, we could make a lot of money, because you could avoid a lot of disasters. And explore the, hey, this thing flamed. I mean, this Air India plane crashed, right? I mean, you have heard these things, right? Why did it crash? Oh, these things happened. You could literally do physics-based stuff to do all kinds of analysis, because the black box recorders have measured. Then you combine it with physics, you could do amazing things. So that's where the power of digital twins is. So now let me talk about the technology. So Ansys has the core physics. We have the leading mechanical solver called Ansys Mechanical or LS-DYNA. We have the leading fluid solver called Fluent. We have the leading electromagnetic solver called HFSS and Maxwell. So we take each of these physics and we can simulate it with the highest fidelity. I mean, if I say this is going to crack, it is going to crack. I tell you not, right? But it requires a 100 million finite element points, right? It will take 10,000 hours. The trouble is that is too long. So what we have in technology is we have these reduced order models. So think of if a 1 million finite element problem, right? Basically, it gets resolved into sparse linear solvers. It is a 1 million by 1 million matrix with sort of some sparse elements. And now you have to solve AX equals B. That AX equals B is an order n cube computation, right, which is taking you forever. Now, looking at that matrix, you going back to your math days of numerical linear algebra, right? There are these things called eigenvalues and eigenvectors and principal eigenvectors. So on that matrix, if I were to take the most important 100 eigenvalues, the principal components, that's 100 of those. Those things are the most, I'll take those 1 million by 1 million vector matrix into a 100 by 100. Those 100 by 100 are the most important things. That's fundamentally what is going on with reduced order models, right? Now, instead of taking order n cube time order 1 million cube, I solve a order 1,000 cube, which is much easier to solve. That's basically what is going on with reduced order models. So we take all the core solvers, build the reduced order models, and do all this funky stuff with hybrid digital twins. Now we have a flow. Now within ROMs, there's all kinds of ROM technology. Again, this is just to impress you. Some of you are in the audience, hey, Prith is just not doing nonsense. There is technologies on linear ROMs, non-linear ROMs, static ROMs, dynamic ROMs. Okay, I have impressed you. So now, we have built this sort of thing, the Twin Builder. So there's just incredible amount of stuff that is going on today, and that's where JuliaHub comes in, right? So we have to take this model of a electric vehicle or a autonomous airplane or this wind farm. So these really complicated systems having hardware and software in it, right? And this combined Ansys Synopsys stuff, right? And you have to do this model building for either brownfield applications. You have a stuff that is there, or for greenfield, right? How do you build the model? Well, I will come to that. It is actually, JuliaHub is a fantastic thing that we are looking forward to partnering with, right? Allowing reuse of existing simulation models with AI/ML. I mean, AI is actually changing the whole world with ChatGPT and others, but it is really changing the world in our area of AI/ML applied to simulation. Enabling scaled runtimes and driving a lot of ecosystem partnership with the likes of AWS, PTC, et cetera, et cetera. So there's stuff that is going on. So let me just focus on the system level simulation part. So let's say you're trying to design an electric vehicle, right? In an electric vehicle, you will have a motor, electric motor. You can actually model it in Julia, which is the high-level system-level model. Now that electric motor is powered by DC power. I have AC power. What do? I take the AC into DC, so I need some converters. Or I take a AC into DC, need an inverter. So I do all this, I'm sorry, DC to AC, need inverter. So I need a battery, I need a motor, and inverters. Then you need to have something that once the motor goes, that motor will connect with a gear, and then it will connect to the actual things, and that's how the car moves. So you could actually go in and model the motor, all of them in Julia, and build a whole electric vehicle simulation model at a high level. But then you say, oh my God, this electric motor has these rotors and stators and all that kind of stuff. Will it really, if I apply this much voltage, my model says that torque will be this much. Is it really that much? Well, we go into Maxwell, which is Ansys, right? And we look at the actual CAD model of the stator and the rotor and all those fantastic Maxwell's equations with all the partial differential equations, and say the torque will be 3.212. In Julia, you said 3.1. No, it's 3.212. But it required now 1,000 hours of compute to get to that accuracy, right? So in this world, what you need is you need a system-level model to do this kind of stuff, but you need to go and validate with detailed models, the 3D models. That is, and if you can bring those things, right, together, that is sort of the interesting thing. Now, in this world, for the last 100 years, 30, 20, 30, 40 years, the leading system-level language has been MATLAB and Simulink, right? But as you guys all know, yes, it is, they are literally the preferred things. You go into any automotive company, they will use MATLAB Simulink as the model-based design thing, right? Then they will, after they pick that motor, then they will go into an Ansys or a Dassault or Siemens to actually model it with the 3D. But with all the advantages that you guys are working on with Julia, right, with the compiled stuff and so on, thanks, Alan, for all the great work that you have done at MIT and the work that you guys have done in JuliaHub. This is where we at Ansys are looking for the partnership, right? So the Ansys Twin Builder, this system, Samir, are you here in the audience? There you go. This is the man. He is the GM for our Twin Builder. He is working closely with the JuliaHub team to say, hey, this thing, can I integrate with and build this system level model, right? And which would be better than MATLAB, better than Modelica, better than all of that is sort of what we are working on. Then building all these things with raw models, scale, I actually need to speed up because I really need to cover some of the other stuff. Okay, so there is other stuff. Sorry, Samir, I'm skipping through some of that stuff because I need to. They'll catch you after for the details. So then the thing is, we are working on an ecosystem where these digital twin models, you can actually visualize it. So those of you who have seen Jensen's keynote at GTC, he talks about the Omniverse. This is this visualization platform. You have a manufacturing thing at a BMW factory, whatever. You can see all those things. So that's that powered by GPUs and so on. So what all these simulation models that we have from Ansys, powered by Samir's twin, is now you can visualize this on the Omniverse. And so you can actually have the physical asset, which is this whatever thing it is, right? Is this the electromechanical stuff. Here's the physical stuff, and you can actually see it on the Omniverse, and you can predict, hey, if this has happened, I put oil and vinegar, this is going to happen, it will show up on the picture. So imagine if NASA had this twin builder and Omniverse in whenever Apollo 13 came down, it would have done amazing things. But we are here today, and I hope there is no more Apollo disasters. Then there's this technology that Samir has been cooking on, this thing called Ansys CoSim, right? Basically, you have a multi-physics simulation stuff, right? You have multiple things, and you have to simulate a distributed system. Some of them are with sort of continuous time, some with discrete time. It is this really complicated stuff, and so we have a technology of Ansys CoSim, which can do this massive distributed simulation together. And I know I'm rushing up because I want to cover the future of digital engineering. So all these things happen. Customers love it. Sorry, Samir. We have used it in Tata Steel. We have used it in glass manufacture. So this thing actually does work. What I really want to talk about is the future. Because this is the academic audience, right? I just want to give you a peek of where are things headed. Where it's headed is in the industrial landscape. You all know we have gone from Industry 1.0, which is mechanization, to Industry 2.0, which is electrification, Industry 3.0, which is the automation and the electronics, Industry 4.0, which is cyber physical, IoT, sensors, etc. We are in Industry 5.0, which is the AI and human and all that kind of stuff. The technologies that are pushing us in that area is AI, all the chat GPTs and clouds and Anthropics and GenAI, the blockchain, the digital twin, the metaverse. Omniverse is the NVIDIA's name for metaverse. Quantum computing, big deal, right? And 6G, right, with all the IoT connectivity. So that's kind of where things are headed from the Industry 5.0, the actual end users. So in that world, the world is moving towards, if you look at how people change from building enterprise resource planning, ERP systems, right? That was a big change that happened in the 80s, to supply chain management systems, to PLM systems, to model-based systems engineering. The world that we live in today is digital engineering ecosystem, right? So in the world of digital, I'm designing an airplane, right? With 100 million lines of C code, et cetera, and you will predict this autonomous electric airplane will fly, right? Boeing is trying to design the 787 Dreamliner set, the future versions, right? The entire thing, the specifications will come in languages like SysML, and output will be a beautiful thing that will, the airplane, right? Fully validated and will run. So in that world, this is kind of the picture of digital engineering. And if there is one picture you want to take, it is this. Yes, wow, I'll take it in with me there, right? Prith, Banerjee talking about future of digital engineering, yes. So in that world, remember I talked about the world of synthesis, right? Synopsys transformed the world of EDA to do electronic design synthesis. I mean, instead of drawing rectangles on the screen, you enter it in RTL, VHDL, Verilog, outcomes, gates, place and route, et cetera, and do the rectangles. That is electronic synthesis. Can we do system-level synthesis? Once you do that, can you virtualize, can I validate? Can you do this with the physical assets, the IT-OT integration? Can I do the digital operations and have the embedded digital twin? So this is the whole journey, and I have one slide on each of them just to give you an example, right? So imagine I come up with a system-level requirement that I need to design a Tesla beater. I'm designing an electric car that will go from 0 to 60 in 1 second and a range of 1,000 miles. I mean, if I could build that car, Tesla will be out of business. And I can, if the cost is like less than $20,000. So that's my requirement. If I could specify a requirement like that, can I synthesize a design? So if you were to work in an automotive company, right, you say, oh, I need to go for a range of 1,000 miles, right? My last car, the electric car that I had, could go only 200 miles, and I had a battery of this size. So if I have to go 3 times as much, I need a 3 times larger battery. That's how a human thinks. I need to go from 0 to 60 in 1 second, right? My previous thing that I had went from, in say, 6 seconds. So I need to go 6 times faster. That one was with the 200 horsepower battery. Now I need a 1,000 horsepower battery. That's how a human thinks. But today, the human is making every one of those steps, saying, oh, for this specification, I think you need a 1,000 horsepower motor with a whatever size battery with that gear. So the human is choosing all those steps. What if automatically I could synthesize all the stuff that is in the human's head, right? All the knowledge is captured, and this is kind of what we are working on. So you do all these things, you say, this is the EV car, and I have actually shown Viral a demo of this, right? There are 6 different designs that automatically came in. Then with JuliaHub, you are actually simulating all of those. This is one case of this combination of this electric car, which has the motor with in-wheel drive, with all the motors in all these wheels in parallel. That is going to be the architecture, right? Or it's the architecture with only front-wheel drive, rear-wheel drive. So all the choices that a human designer have done automatically, and that's system-level synthesis. The second one is virtual validation. You are designing this car, right? It is going on the streets of, driving from Los Angeles to Las Vegas, right? In the heat and so on. It's just super hard, and then the thing is going over this thing, right? So how do you actually test, virtually test, before you build that car, that it will actually work, right? So the normal way that you do is they do the unit testing. Test the motor, test the battery, test the gears and so on, and then you do physical testing, you do the combination of physical testing and so on. The future is all virtual. Because if I'm saying, if the world is governed by the laws of physics, if Navier-Stokes equation doesn't lie, if Maxwell's equation doesn't lie, you don't have to build a physical prototype. Go to 0 physical prototyping, right? And we have actually done things with digital twins. The picture is, if you could show those videos, it actually shows here is a car going right from Las Vegas to whatever, really hot things over this highway, and is there overheating happening or not, right? So you could actually validate it. Then you have this IT-OT integration, right? I'm just going through this, right? You have all these different things, and you put sort of sensors, you put PLCs, et cetera, et cetera. So there's the OT part is having all these Modbus, OPC, UA, all those standards that you have. And then you connect, use all the latest Ethernet technologies developed by Bob here, right? And this is the world. The world is MQTT, broker, et cetera, et cetera. That's how, in a real system, you are actually building these things with IT-OT integration. Then you did the whole digital operations. I'm flying this airplane from New York to Kathmandu, or New York to Mumbai, right? And I will do all this thing, right? This is going this plane, et cetera. I have all the sensors. So doing this whole thing with digital missions engineering, digital twin, that's sort of digital missions engineering. The last thing is digital twin. This is kind of where somebody is headed with this stuff, right? So we did a little interesting project in this Covisa joint work, right, with companies like Bosch and all. So imagine you are driving electric car, right? And you say it's like only 30% charged. Oh my God, if I don't find a charging station, by the time this thing goes, right, I am toast, because I am on the highway, I need a charging station. So this is called range anxiety. So let's imagine that I'm a driver and I have connected to all the power and electronics and AC and all the kind of stuff, right? On the thing says, I have to go on 30% things, and with that, I could drive only 100 miles, but my charging station is like 200 miles away. What the heck do I do? If you're like me, say, oh, sure, come on, turn off the lights, turn off the AC. So you do all those things, right? This thing would say, Prith, just relax. Don't turn on the lights. Don't turn on the AC. You just reduce the AC from 75 to 42, and you'll be fine. And you're completely crazy. You just go in with the last amount of juice, go into a charging station, you're done. If you could predict it as well, that would be amazing. So it's an example of an embedded digital twin. I thought this was an entertaining morning. So what I talked to you about is the concept of digital twin, which can be done with pure data analytics or with simulation, and I think the world is headed towards hybrid. I am biased. I think we are well positioned. Samir and we agree on that. But the future is about this digital engineering area, and this will literally be powered by JuliaHub. I kid you not. So we are excited to work with JuliaHub and all of you in the audience. So thank you very much for your attention. Thank you.
Questions for the speaker? I'll start handing the mic.
Yeah, thank you so much for everything that you've been, I think that we share a lot of the vision here, but what I'm really curious to hear from, your experience here is, we've put together this idea of, here's how digital twins can change the world, and it has the, pieces with IoT and simulation, What is the weakest link of this whole connection? And how should we prepare for it, right? Is it, there's a few things that come to mind. Company structures might have it so that way the people who design assets might be different than those that maintain it. Is it something with IoT security issues? Is it ability to scale simulation? Like, where in this are you looking and you go, oh, I'm scared that this is the weak link, and how should we think about what we're doing to handle that issue?
Unfortunately, it's not a simple thing with just the IoT security. It is actually a range of the things that you can cover. But I think I painted a picture that if you could do hybrid digital twins, right? So pure physics-based digital twins, even though, I work for Ansys or Synopsys, we would like to say it just is not accurate enough because it doesn't capture the bird strike that struck this thing, right? So unless you can connect it with the data from the actual hardware, right, from the actual sensors, it will not work. So you need to do this. The difficulty here is that you have to be connected to the actual IoT structure. So I saw that you listed ASML as one of your partners, right? And Viral and I kind of talk about it, right? So let me give you a classic case of something that we are working on, right? A digital twin of a semiconductor manufacturing plant. At TSMC or Intel, right? They have these massive things with the hundreds of equipment, 5 equipment from Applied, 10 equipment from ASML, 15 from KLA Tencor, all these different equipment, right? Now, imagine if you create a digital twin of each of the equipment. In a semiconductor process, right, there's like 200 processes that you have to do. You have to do chemical vapor deposition, then you do ion implantation, et cetera, et cetera. And you do this complicated stuff, and then out comes the Blackwell chip, right? And this thing, the yield is only 1 in 100 work, right? So all the others are kind of wrong, right? And so you have a line, and you have bad stuff coming out, right? I have a yield issue. How do I fix it? So if I could come up with a digital twin of that manufacturing plant, right? I can improve if you can just improve the yield by 1%, it's like billions of dollars, right? But you can. So, in this world, what happens is, if you could do a digital twin of an Applied equipment, and actually Applied is our customer, ASML is our customer, we can build a super accurate model of that Applied equipment, that epitaxial process, etc. Right? But to make it work with hybrid, you need the Applied sensor data to come in, and so on. Now you put the Applied equipment TSMC, they'll say, hell no, I will not let you connect the data from applied to this because this is my data, right? So the real practical stuff, I mean, the academics we know, if I could collect the data, right, it's there, but you cannot, I will not let you, right? So you have to, what we are working on a solution is to say, okay, TSMC, I kid you not, this is exactly what we are doing. TSMC, you will not let Applied have the data, but we have helped Applied build the equipment, right, with our models. So I have a digital twin of the Applied equipment and that epitaxial whatever process. Just let us have access to your data. I mean, and I will give you this thing, you do this on your stuff, and it will be so much better, right? So this is the case we are making. We are not there yet, but the challenge is this siloing of the stuff, which happens in real manufacturing. If you would crack that nut, well, it's openness and so on. People talk about openness. The real world is Applied doesn't want to because they're all competing for this thing, right? So that is the real challenge. Sorry to give a really convoluted answer, but it is really hard problem.
So that was a fantastic answer. Any other questions for the speaker?
Oh, I'm so disappointed. Nobody cares.
No.
I love it when a speaker gives a vision of the future, because that's, of course, the hardest thing to predict, as they say. So you've been a professor, you've been a technologist. As a professor myself, students often come to me, and I get the feeling that they are figuring out a course of study based on what made sense last year. Do you have any advice for students who want to look into the crystal ball and what will be most relevant a few years from now?
That's a great question. And the book that Viral referred to, right, called Innovation Factory, I am not shamelessly promoting the book. I'll just say that the thesis of that book is that large companies like ABB, Schneider, HP, Ansys, etc., right, they do a good job in the Horizon 1 innovation. I have my Fluent, what feature do I need in Fluent next year, right? That we nail it, because that's an incremental stuff, right? The adjacencies, which is Horizon 2, is sort of, yeah, I have a thing working on-prem, I want to go on the cloud, or I have a transformer in North America going to China with 220 volts. That also people know. But it's very hard for a company that is making laptops, Macintoshes, to come up with a brand new thing like an iPhone. So it takes an Apple to do those kind of stuff, right? So what I say in my book is, if companies want to do it, they really need to partner with the Allens at MIT and the startups like JuliaHub. And so this is literally what I kind of say. But in my final chapter, I say, you are all students, right? You are professors. And so when Synopsys started EDA, or Ansys started simulation 50 years ago, the computer that I had 1 megaflops of power, had 32 megabytes of memory. So I wrote my Fortran code with column major order to do this stuff, with all these stuff, right? Based on the computing that I had at the time. And then the world of parallel computing came in. Oh, now you can do threading. So I can take my Fortran code, do shared memory threading with this. Now I did, I have message passing on the Cray, so I can do MPI. So I took that Fortran code and chunk into domain decomposition, do this. And now GPUs came in. Oh, now I should take this Fortran code, now try to GPUize it. Then quantum computing came in. Now all these qubits are happening. So the real challenge that happens is you develop some product based on the technologies that were there at that time. Now, the students graduating from CMU, UP, MIT, Illinois, Georgia Tech, right? In 2025, the technologies that you have are cloud, IoT, blockchain, ChatGPT, GenAI, quantum. Now, if you say, I want to do a startup which is an EDA technology leverage with GenAI, quantum, GPUs, etc., it sounds fantastic, right? You put everything in the kitchen sink. The smart person, right, like Bob or Alan say, it's a combination of blockchain. If I took blockchain and quantum and GenAI, I did this here, that would be amazing. So think of these individual technologies as pearls. You have to create that necklace, string together those individual points, and do something like an iPhone that the world hasn't seen before. So, I mean, the iPhone technology put together a bunch of technologies, right, in a beautiful necklace. And that is what the students at MIT, you should advise them, right? You have all these amazing technologies coming, and not all of them are available. Like quantum, we are working on, I mean, I kid you not, all the technology I mentioned, I have got in the CTO office working on those things, right? But my CEO says, why are you doing this? Because I don't know what the necklace is. The future of digital engineering, this system-level synthesis is actually leveraging AI, quantum, this, that, etc. That is the exciting thing for your students.
I think at MIT it won't be the necklace, it will be the jewelry store.
I agree. Thank you. Thank you.
Thank you. I think there are a few more questions, but
I am around.
Yeah. Please do find Dr.
Take
Banerjee.
selfies with me, post them on LinkedIn. I'm just kidding.
With that, let us thank the speaker again.
So, some of you might have seen our announcement of the Dyad product. It's Dyad is a new DSL for modeling and simulation, and we're actually gonna have some demos about it, show you what it does, and hopefully put a little bit of sort of detail into some of the things that Prith talked about in terms of how do engineers actually go about building some of these workflows. A lot of the motivation for this stems from, for work in the Julia community, right? That as we started talking to customers, of the kind that Prith talked about, a lot of them are like, Julia's great, Julia's awesome, but I need tools with higher levels of abstraction that will allow me to accelerate my product design, bring my products to market, and check all the boxes for safety, regulatory, all of that. So Dyad is a tool. So Dyad kind of combines a lot of, it's a dyad, right? It's a dyad of many things, or it's many dyads. Brings engineers and software engineers together. It brings, math and physics together. It brings, data and model-based design together. So we felt like this is an appropriate name for this product, is that it's a dyad. It's bringing two different cultures together. So here's what Dyad expects to do. It's accelerating a lot of critical industries. We spoke about a lot of these aerospace, automotive, high-tech industries. AI is everywhere. I was just talking to Chris today. I believe that everyone in this audience is already heavily using AI in some form or shape, at least when it comes to Julia coding. A lot of people have actually told me that it works quite well with, with Julia, most of the coding tools. And Chris actually topped it off last night by showing me 25 TMUX terminal screens on his phone.
32.
I think you might have added some money into your thing there. So he said he woke up and he had 6 more PRs that were merged by then. So we are entering a brave new world. But everything that we're doing with Dyad is actually built on all the open source tools and technologies that we've spoken about for several years, last decade at this conference every year. And we are sort of thrilled to show you some of that in action now. Uh-oh, I want to actually pull this whole thing up. So again, for those of you who are not familiar with engineering product design, this is the world of product design, right? You have requirements on the left-hand side, you have verification, validation on the right-hand side, and then your digital twins in operation. And I think that the thing that is relevant, I think, to this audience is that the top parts of this V cycle are actually modeled as ODEs. And then as you kind of get into the details, you get into DAEs. And then as you actually start doing component level design, you get PDEs. And while the PDE world actually has a lot of amazing software available from a lot of industrial vendors, the ODEs and DAE space is actually fairly light. And it would probably come as no surprise to you that Chris and I decided to focus on this world as we go forward. And we have over 50 talks at JuliaCon over the next 3 days that will touch upon the underlying mathematics, the underlying physics, the software engineering. How does Julia make small binaries? How to constrain the size of the system image? Every single thing that we all grapple with here is actually coming together into actually building real products for physical products, right? And so on. I'm going to move a little fast here. So our next thing, Chris is going to talk about the demos, but one of the cool things about Dyad is that when you talk to engineers, they're like, Julia's cool, but it's all code. I can't work with code, right? Engineers are not software people. You need to have a GUI. You need to sort of have an intuitive grounding in the kinds of models you're building. And I think Michael Tiller, somewhere in the room, he's the architect of Dyad. If you see him, oh, he's all the way at the back there. If you see him, ask him anything you need to about Dyad or about the why of Dyad. But this is the fundamental sort of push and pull, right? That we want something that's a first-class coding environment. You want Cursor, you want Claude Code, you want the 32 terminals that Chris is running, to design every component of your airplane while he's sleeping. But you also need to be able to see what was produced and verify it and validate it and do all of that. And Dyad is our answer to all of that. So without further ado, Chris.
Yeah, so here's a view of Dyad in action, right? So what you're looking at is we're constructing a digital twin of a DC motor. So this is actually being built using physical components. So you're putting down these components that have these physical equations. It's generating what's known as a differential algebraic equation that is all the physics involved in the object. And what's happening here, though, is someone who might not know as much about how the inertial elements work, how maybe the resistor or the inductor, you can piece together these models that someone else has already built. You just say, hey, connect these. This resistor goes to this inductor goes here. And what you're doing is you are working at a coding interface or at a GUI interface, right? You're putting in these values and you're saying, hey, this is my friction coefficient, but it's actually building a code under the hood. And it's actually bidirectional. If you modify the code, it actually will modify the GUI as well, right? And so you can also then look at this and say, oh, I can, you can interface with all of your Claude components or all of these AI tools as well. And now what this is actually running now is it's now going to do a PID auto-tuning analysis. So doing this kind of controls analysis on the model that we've created. Now, the cool thing about this is that these analyses, right, the fact that, oh, hey, it's able to do this noise sensitivity analysis and all this is done with an interface to Julia code. And so every one of you out there that has a Julia package, if you want to be able to put your special things that you do, your surrogate generator, your digital twin pieces, if you want to make those work with the Dyad GUI, there's a direct interface, so that way we basically just say, here's how you expose your code, so that way any possible analysis can be done with the model. Because what we really feel is the future is to be able to make all of the ways that the open source community is building out new ways to analyze models with all the pre-made models that are actually being built with high fidelity within these companies. I think that when we get these two together, then we'll be in a place that we haven't been before. And we're also then putting this together with automated code generation, so that way the devices that we build and tune through Dyad can actually be put directly onto airplanes, cars, and be able to be the thing that is running the future. And so that is what we're really piecing together, something that is a graphical coding environment or a graphical modeling environment with a coding interface, tying this together with all the tooling of scientific machine learning to help improve the models that are generated, but also the generative AI tooling, so that way all of the code in the back end can be improved and the scale is run. And so basically this, it's not about just being able to build a digital twin, it's about being able to have a system where digital twins can continually start to improve themselves. And you start to have this run on a cloud system, the data's coming in, and the digital twin is just improving, and becoming more and more real because it is actually out there and living in the environment. And so we're starting to see this so this was a model built by Ben Chung, and he'll be giving a JuliaCon talk on other aspects. But here's, for example, an HL-20 lifting system, which is a model of one of the older spacecraft of NASA. And you can see that this GUI is able to build out these large-scale models of these pieces. But then we can expose these gigantic models of realistic systems as just a component. And you start to drag them in there, and we start to say, okay, here's a realistic battery, here's a realistic car. Piece it all together, and now what is the mileage that my Tesla will get 10 years from now after the battery's degraded? And these are the questions we can start to answer and be able to know, are we designing our vehicles appropriately? But for everyone who's here, it's all built on the Julia tools. And so if you want to be able to integrate with the system, right, if you're using Modeling Toolkit, we have APIs to be able to say, hey, look, here's how you can make sure your Modeling Toolkit type of code, here's how you can integrate with Dyad. And if you're building analysis tools, if you're building things that make interesting plots, there's all of these ways to be able to say, if you want folks within, Ford or, any company that's potentially going to be using these systems in the future, here's how you integrate with the graphical user interface, so that way your tools, and all your things are directly exposed to those who want to be using graphical interfaces. Because this is what we see in the future, right? there are people who are using point-and-click interfaces, and there's people who are using code. I think that both will always exist, but making it so that way those two can tie together, and importantly, bring in the open source community, I think that that is where we make a play that no one really has been able to do in the past, and that's how we then change how all things will be designed in the future. So, and we're integrating this directly with a lot of the tooling that, this is really kind of changing the world, right? So here, this is a cursor integration that is working directly on the Dyad code. You can see that it is figuring out with this model, which is a model of an active suspension, how to be able to do the PID auto-tuning. It's understanding and giving out information about, how this controller should work. And it actually has made a change to the code to be able to put a controller piece in there, and then it's going to run a transient analysis to be able to tell you, oh, this is actually the optimal control signal for this for the force on the seat, right? Because the idea here is, could we have components where the code is actually improving, right? So you build a car once, but if the car is actually half software, can we make it so that way you can make a simple car, a cheap car, but because of software, it's actually more luxury than the most expensive vehicle you could build? Can a software update take a $10,000 vehicle and make it feel like a Porsche? I think that this is possible, and that's the future that I think that we can all head towards. And this is what we're enabling through Dyad. So if you haven't tried it out yet, please check out Dyad. It is a domain-specific language that interacts well with Julia. The components that you build, it's all generating Julia code, and so you can actually see, oh, what is it compiling to? How do I run with it? So everyone here in this open source community, if you want to get familiar with everything that's going on, give it a try. We're going to have a lunch and learn later today. Yeah, and Dyad, what? Yeah, and Dyad is actually source available, so we made it so that way the compilers and these kernels involved, you can take a look at the code that is in there, and then a lot of the standard libraries are open source as well. I will say that, there are certain libraries that we're using as a part of the productization, but there's a lot of open sources being integrated into the way that we're doing this, specifically because we think that this is the way that, we can help grow with the Julia community. And so with this, there's a whole lot of talks that are going to be happening at JuliaCon. Take your pictures. Basically a lot of things that are going on related to scientific machine learning, differential equations, and all the things involved with modeling toolkit, aerial vehicles. These are all going as part of this push for Dyad to really pull the Julia community from things that we're doing in academic space to the thing that is now running the next airplane and the things that are running the next automotive. So thank you, everyone. And if anyone wants to if you're interested in, using these tools, but also if you're just interested in, hey, how could I be a player in this change that's going on in how Julia is growing into the, big industry player, please come talk to us. We'd be happy to, tell you and, and have a conversation about, how we are interacting with this whole community and how things are changing and how you can be a part of everything that's growing. So thank you very much.
Thank you to JuliaHub for being a diamond sponsor at JuliaCon 2025. Are there any questions? We could do a quick question. No, I mean...
For the stream.
You should probably use the mic for the stream. Yeah, thanks.
So thanks for the inspiring talk. What's the are there any possibilities of us or the Julia community also, let's say I want to come in with another types of blocks. I come from quantum modeling, so I can see this GUI also be helpful to build systems in there. What's sort of the possibilities for that?
Yeah, fantastic question. So all of the Dyad repositories, they're actually Julia repositories with a Dyad folder that is basically giving it the information that it needs to be able to represent these components within the graphical user interface, right? And so if you're already using Modeling Toolkit, there's actually, the change from Modeling Toolkit to Dyad is not very difficult. I would say check out the Lunch and Learn, where we'll show what some of these Dyad libraries look like. Again, they're just Julia repositories. So if you add that Dyad folder to your library, then boom, someone will be able to grab your library from open source and be able to effectively integrate it with the graphical user interface. So yeah, I mean, and so there's the integration as model components, and then there's also the integration as analyses, right? I mentioned that, you know, there are these controls analyses that we can run, right? You know, for tuning autocontrollers. So if you're someone who's, you know, working on, instead, like, here's a new machine learning method for better reduced order modeling, if you want to make this so that way it's available to this larger population, you can also make that custom analysis. There's an API for that, and it just generates the text boxes for the information it needs, and then boom, now you're directly integrated as well. So we specifically developed this because, you know, we work a lot with the Julia open source community, and we want to make it so that way everyone's work could be, you know, integrated, so that way, you know, you can get more people using your stuff, more people who are citing you, and you know, finding out more about how this is being used in the real world, right? So we definitely want to help talk to you about, you know, how you can help make that connection.
Actually, I just wanted to, you know, I think that was a very good question, right? Like, you know, whether it's quantum or whether it's a systems biology, right, or QSP or any of the other modeling domains that I know that a lot of the folks here have talks about. One of the things that you see with existing tools or the legacy tools is that, you know, it's a two-tiered system, right? Like, the people who design the system actually have incredible power to add features and functionality and models, but the end users actually get a black box. And I think the thing that's different about Julia is, you know, as we all know, is that it gives you the same powers as, you know, the compiler writers, the standard library authors, or the end users have the same level of access to the internals. And that's the same sort of idea within Dyad as well, that everything that you see here with the GUI, with the models, is fully extensible by the user. So there is sort of no that can do special things. You know, the end users can do all of this and completely extend all aspects of the system.
Thanks, Viral. With that, I conclude this particular session, so let's thank the speakers again. If you're